let's see, we're getting down towards the end, and so we're about to start our last chapter here, and this chapter is called Solvability by radicals. So, as I'm sure you know, the whole point of Galois theory in the end, right, is to show that there exist polynomials for which you can't find, right, you can't factor, you can't find the roots of the polynomial. And so we need to make all of this precise now. And so here's the idea. If you have a non-constant polynomial, so let's say given let's say non-constant f with coefficients in some field, what we would like is some sort of formula, some sort of algorithm that will produce the roots of the polynomial. And so let's say this, given non-constant f, we want a formula slash algorithm for producing the roots, or let's say this better, an algorithm that produces the roots of this. But how this algorithm works? So that takes as input the coefficients of the polynomial f. So you say, what determines the polynomial? The coefficients determine the polynomial. And I'll say, and after a finite number of steps, gives all solutions to the equation f of x equals 0. Okay, so there's the idea. This is what we would like. This is what they've been searching for, going back into antiquity. Right? They understood what polynomials were, and they wanted to find the roots of the polynomials for various reasons. Now, okay, so we need to say a little bit more about what's legal here when it comes to this algorithm. So, meaning we need to somehow arithmetically understand or be able to handle, right, the algorithm itself. So what do we allow when it comes to this algorithm? Well, we allow field operations, right? Addition, multiplication, division, subtraction. Those are all good. Plus taking nth roots, right? So each step of the algorithm should only involve addition, subtraction, multiplication, division, and taking nth roots. And of course, the classical example is the quadratic formula, right? So what does it do? Well, it says, okay, here's your polynomial. F of x equals ax squared plus bx plus c. Let's say for now, it could be real coefficients, but let's just say for now that we're viewing it in q bracket x, right? So we have rational coefficients. Then what we get is that these solutions, right, x equals negative b plus or minus square root of b squared minus 4ac divided by 2a. And so this formula says, okay, what do? Tell me the coefficients of your polynomial. I will tell you in one nice quick formula, here are who the roots are. Now, let's get a little more explicit here. So let's let alpha equal square root of b squared minus 4ac. Now there's two possibilities. If alpha is a rational number, then the polynomial splits over q. So if alpha is in q, now what do we mean by that? So that is there exists alpha in q such that alpha squared is equal to b squared minus 4ac, then f splits over q. If not, then what? If not, then f splits over q adjoin alpha. So if not, then f splits. Right? How do we find a splitting field? Adjoin the roots. Well, if you join the plus, you don't need to adjoin the minus here. Right? And everything else will happen in q. So then f splits over q adjoin alpha. Okay, so this idea right here is going to motivate our next definition. Let L over K be an extension. And let's take alpha in L. Now, if you can raise alpha to some positive power, alpha squared, cubed, fourth, whatever, some root, some natural number, and it lands inside K. So if alpha to the n is an element of K for some n in the natural numbers, then alpha is radical over K. Right? So you can think of it that alpha is the nth root of some element of K. As an example, the imaginary number I, right, that's a complex number, so this is radical over Q because by raising it to the second power, right, we get an element of Q. So now, our next definition is going to make use of this idea of a radical element. So an extension L over K is radical if essentially, and I'll write it down precisely in a second, but it's going to be radical if you can build L by successively adjoining radical elements. Okay, so let me say this precisely. So this is radical if there exists a sequence. So a sequence of intermediate fields. And so it'll go like this. So let's call K equal to L0 contained in L1, contained in L2, blah, 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 contained in L sub n. I used an n here, L sub m, which is equal to L, where at each stage, the L, let's say it like this, Li is equal to L, wait, Li? Oh, I minus 1, yeah, okay. L sub I minus 1 adjoin alpha sub I, where alpha sub I in L sub I is radical over L sub I minus 1. Okay, so what are we saying then? We're saying that L, for example, okay, let's just take the step by step. So L1 is equal to K adjoin alpha 1, where alpha 1 raised to some power lives in K. Okay? So in fact, let me just draw sort of a picture here. All right, so what do we have at the first stage? L1 equals K adjoin alpha 1, where alpha 1 lives in L1. I mean, that's kind of silly to even say that. Of course it does. In fact, let's just say it like this, where alpha 1 raised to the n1 lives in K. Okay, so there's the first step. And then you have L sub 2 equals L1 adjoin alpha 2, where alpha 2 raised to some power n sub 2 is in L sub 1, right? And you keep going, building L by adjoining one at a time a radical element. Okay, and then our next definition, a polynomial f in K bracket x is solvable by radicals if there is a radical extension L over K where F splits over over L. And this is the definition that we're looking for that formalizes the idea of having an algorithm or a formula to find the roots of the polynomial. When the polynomial is solvable by radicals, what it's saying is that it splits in a place where you to get the element, let's say to get the roots, right? What do you need to do? You need to, or to let's say it this way, to describe the roots. What do you do from K? You adjoin radical elements, and so the roots of F can be described or can be not described, can be built by adjoining radical elements to the base field, the field of coefficients right here. And so, for example, so the polynomial f equal to ax squared plus bx plus c in q bracket x is solvable by radicals. The reason is that f splits over q adjoin b, square root of b squared b squared minus 4ac, and square root of b squared plus 4ac squared lives in q. In other words, q adjoin square root of b squared minus 4ac over q is a radical extension. And so the question that the Greeks and everybody, from that time on who wanted to understand the idea of factoring polynomials, right? Even though they didn't have this term, the question is, are all polynomials in the classical sense, all polynomials over Q solvable by radicals. So, according to the quadratic formula, the answer is yes in degree 2. In fact, let me just write down a little bit of a history here. So what we have is so I think this is the guy that came up with the quadratic formula, or gets the credit for quadratic formula. How do you spell this? KHWA, RIZMI, says yes in degree 2. This goes back to around 880, right? That's where the quadratic formula comes from. In degree 3, the answer is also yes. So this goes back to Del Ferro, who apparently proved this first. So yes in degree 3. This goes back to around somewhere in the 1500s. And apparently he did not write down a proof of this. And these two guys, so he didn't publish his proof. And then these two guys, I forgot the history. There was some sort of, battle. Cardano and Tartaglia. I meant to look this up, but I forgot. So these two guys, they had some sort of almost like a duel, like a mathematical duel. I can't remember the story exactly, to actually to figure out the formula for the degree 3 formula. So if you have a degree 3 formula, it's kind of complicated. You can look this up though. But there's a formula that tells you who the roots of a degree 3 polynomial are. You give as input the coefficients of the polynomial, right? rational numbers, and this formula spits out the roots. It's definitely more complicated than the quadratic formula, but it still exists. In degree 4, this guy Ferrari. So this is yes in degree 4, around 1550. Then in degree 5, it goes to Abel and Galois. Separate work, so no in degree 5 and above. Same thing, no in degree 5 and above. This one's in around 1820. I want to say 1823 and 1825 is when they did their work to show that there is no algorithm. There exist polynomials that are not solvable by radicals. Okay, so our goal now is to show exactly what I just said. There are polynomials out there that are not solvable by radicals, which means they do not split over, right, or there's no radical extension for which the polynomial splits. And so what that tells us then is that in general, there is no formula that will handle all possible degree 5 and higher polynomials and tell us who the roots are. There are polynomials of degree 5 that are solvable by radicals, right? But not all of them are. There exist polynomials that are not. Okay, so that's where our journey is taking us now. We want to see why the answer is no. Okay, so we need some group theory now. So a group G is solvable if there exists a, it's called a subnormal series. So if there exists a series that goes like this, starting with the identity, we'll call that G0, normal in G1, normal in G2, normal ... normal in Gn, which equals G, where the quotient Gi mod Gi minus 1 is abelian for each I, for each I. So a group is solvable if there's this collection, this series, right, of subgroups where each one is normal in the bigger one. Now, we're not claiming that the G's, the little gi's, are normal in G. They're only normal in the next successive one. Right, so when such a series exists, then we say that the group is solvable. Now, it turns out, so in the case that G is finite, we can modify the definition. It's equivalent to the following definition. So in the case that G is finite, there is an equivalent definition. So it goes like this: the finite group G is solvable if there exists a subnormal series. So a series one equals G0 normal in G1 dot 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 normal in Gn, which equals G, where each quotient is cyclic, where Gi mod Gi minus 1 is cyclic. So a couple of examples. Abelian groups are, of course, solvable. Why is that? Well, if you have an abelian group, right, then you have this sequence right here. 1 is a normal subgroup of G, and of course G mod 1 is abelian because it's isomorphic to G. Another example, D4 is solvable. And the reason, so let's let sigma in D4 be an element of order 4, right? So remember, D4, that's the symmetries of a square, and so all we need to do is take a rotation, a 90-degree rotation. There's an element of order 4. So then, here's our series. We have the trivial subgroup is normal in the subgroup generated by sigma, which is normal in D4. Why is that? Well, the subgroup generated by sigma, that's a cyclic group, so it's abelian, which means that this mod this is isomorphic to this, which is abelian. And then this has order 4. This has order 8, which means that this is an index 2 subgroup of D4. That tells us then that, that it's a normal subgroup, right? Index 2 always is normal. And then when you take the quotient, it will be isomorphic to Z2, which is an abelian group also. In fact, so yeah, let me write this out. We can say and subgroup generated by sigma mod the trivial subgroup isomorphic to Z4, which is abelian, D4 mod subgroup generated by sigma isomorphic to Z2, which is abelian. And notice they're cyclic, so I can work, because we're working in a finite group, we can use this definition if you like. I talked about this back in Math 481. It was like this. So this example, every finite group of odd order is solvable. This is due to Feit and Thomson. And remember, this is the one where I was talking about the usually when you publish a paper, it appears in a journal, and a journal typically has 4, 5, 10 different articles in there. This one took up the entire 255 pages of one journal. So this appears in the Pacific Journal of Math, 1963. and it takes 255 pages. This is a big deal right here. So every finite group of odd order is solvable. And this was used then to help in the classification of finite simple groups. Next example, if n is greater than or equal to 5, then S sub n is not solvable. Now, what's the reason? AN is a simple group, right? So we know for n greater than or equal to 5, AN is simple, and it's also not cyclic. It's just a simple group, not cyclic, and so it follows that that AN is not solvable, right? So so since it's simple, it has no non-trivial proper normal subgroups, right? So we could never, right? There's no one that can go over here, right? There is no such thing other than the identity and AN itself, right? And so there is no subnormal sequence for which we get abelian or cyclic quotients. Right, the only normal subgroup is right there, and when you take the quotient, you get something that's not cyclic. Now, okay, fine. So AN is not solvable, and what we will see, that subgroups of solvable groups are solvable. And so if Sn was solvable, it would force AN to be solvable, but we know it's not. And so for n greater than or equal to 5, S of n is not solvable, and there might be something important about that 5 right there. Okay, so for n greater than or equal to 5, Sn is not solvable. It turns out that both S3 and S4 are solvable. So S3 is solvable. Why is that? 1 is a normal subgroup of A3, which is a normal subgroup of S3. And when you look at the quotients, right, A3 mod the identity, that's going to be isomorphic to Z3, which is cyclic, and S3 mod A3 is isomorphic to Z2. Right, so we have a subnormal sequence for which we get cyclic quotients. Oh, sorry, I said Sn. I should have put S3 there. Also, S4 is solvable. And the reason, let's see who we need here. Let me write a symbol here. So let's let's call it B. Let's be the subgroup consisting of the following elements. 1, so the identity, and then 1, 2 times 3, 4, 1, 3 times 2, 4. I'm just using disjoint cycle notation here, and 1, 4 times 2, 1, 4, not putting commas here, times 2, 3. Okay, so there's our group. This is a subgroup of S4. And so then here's our subnormal sequence. We've got the identity is a normal subgroup of the cyclic subgroup generated by 1, 2 times 3, 4. Which is a normal subgroup of B, which is a normal subgroup of A sub 4. We showed this back in Math 41. This subgroup is a normal subgroup of A4, and then A4 is a normal subgroup of S4. And then if you look at the quotients here, right, so this one, this mod, the identity, the quotient gives is what, this has order 2, so that gives me a Z2. This has order 2, this has order 4, so this one gives me a quotient of Z2. This one has order 4 sitting inside A4, which has 12 elements, so the quotient has to be Z3. And then the quotient here, this has index 2, so that's a Z2. Okay. A couple of facts that we'll need. So theorem 7.1, this is called usually called the second isomorphism theorem. I don't think I had you prove this one in Math 481. So let's let, I can't remember now, so let's let G be a group, and we need a normal subgroup, so N, a normal subgroup of G, and H, just any old subgroup of G. Then H intersect N is a normal subgroup of N. Oh, sorry, not of N, of H. H. And when we look at the quotient H mod H intersect N, that's isomorphic to H, HN? Oh, NH mod N. So this one's called the second isomorphism theorem. I'm not going to prove this. You can find the proof in any algebra book. Also, I want to write this one down. So this is usually referred to as the third isomorphism theorem, and I think this is the one I had you prove in class as a homework problem in Math 481. So isomorphism theorem. So let's let G be a group. And then I need a couple of subgroups, both of them normal, so H and N, both normal in G, and then I think I want H inside N or any, oh yeah, H contained in N. Then H is a normal subgroup of N, and when we look at the quotient, N, well, fine. N mod H, oh, right, is a normal subgroup of G mod H. And when we look at the quotient G mod H mod N mod H, that's isomorphic to, why does this look weird? No, that's right, N mod H, isomorphic to G mod N. So this one you proved in class. And it's a straightforward application. In fact, both of these are straightforward applications of the first isomorphism theorem. Right? So they're, in a sense, they're corollaries to the first isomorphism theorem. But they're important in their own right, and we're going to need these facts for what we do in the very near future. Now, the next theorem that we have, what are we doing on time here? Right. Yeah, this is a good place to stop because this next theorem is going to take us to prove this one. Oh, it's going to take... I guess I can do it in one long lecture. So, okay, so we'll stop here and we'll see you next time.